Can you hear me okay and see my screen and my cursor?
Yes, we can.
Okay, great. I will get started. Okay, great. My name's Sam Upton, and I'm a final year PhD student at the University of Southampton. And I'd just like to say thank you to the organizers for giving me this opportunity to speak about my research today that I've done with my supervisor, Adam Pound. So I'll be talking about covariant and coordinate punctures for second order gravitational self-force in a highly regular gauge. That's quite a wordy title, so I'll break it down and explain what I mean by that. So first of all, I'm going to talk about the issues that we encounter when we look at second order self-force. Now, Ollie gave a nice intro to self-force, but I'll just recap some of the things as well. I'll give an overview of the highly regular gauge and discuss why it alleviates some of these issues that we find at second order. The fact that it's less singular and it allows us to have well-defined second order Einstein field equations that include the world line of the small object. And finally, I'll talk about how we can implement these the highly regular gauge in, say, a puncture scheme. So I'll give a overview of self-force. So you'll have seen this picture immediately before in Ollie's talk. So you can see here that for large mass ratios, we use the self-force approach, where the small object is cast as causing a perturbation in the space-time of the background object, so of the large black hole. So this would be the background. This would be the metric of the large black hole where it on its own. So that would typically be Schwarzschild. And then you have these perturbations on top caused by the presence of the small object. And then how the object moves, it moves as a geodesic in the background. And then there are higher order corrections, which is the self-force, which move it away from geodesic orbit. And we can split these force terms into a conservative and dissipative part. So I should note here that although we generally use self-force for higher mass ratios, there has been recent evidence that shows that we can get actually quite close to mass ratios of, say, 1 to 10, and maybe even 1 to 1 in certain areas of the parameter space. And to track the orbital frequency correctly, we need F1 and a certain part of F2. So it's been known for about 15 years that second order self-force is crucial for precise parameter extraction from MREs. It's not that the first order self-force gives you something and the second gives you a bonus. You really need both the full first order self-force and this specific part of the second order self-force in order to actually extract parameters from MRE data. So one big hurdle that I've been focusing on overcoming in my PhD is the strong divergences on the small object's world line. If we split our perturbations into regular and singular pieces, these singular pieces, they encode essentially the multipole structure of the small object. We can see they go like m over r, and then at second order, m squared over r squared. Now this has the consequence of being incredibly singular. So when you want to solve things numerically, it becomes very hard. You have delicate numerical cancellations that you have to deal with. And also it means that your field equations aren't well defined on the object of the small object's world line. However, in the regular gauge, this is less singular. In fact, if you split up the second order singular piece again, you can find that you eliminate that most singular m squared over r squared piece. In fact, the most singular parts of these two objects, it goes like m times a smooth function over r, and then you have m squared times r to the 0. So you've immediately got rid of this r squared, 1 over r squared piece. So how do these problems at second order manifest? Well, the second order Einstein field equations have this form. So if and the quadratic Einstein tensor has this form. So h times the second derivative of h plus a derivative of h squared. So if hs1 goes like 1 over r, that means that d2g will go like 1 over r to the 4. So this causes huge problems when trying to solve numerically because of the strong divergence. And as I've stated before, it's ill-defined on any domain that includes the world line of the small object. So how does the highly regular gauge fix this? Well, the HSS term goes like r to the 0. So we know that if we take two derivatives of that, and then it has to be because HSS is constructed of singular times singular pieces, it has to be sourced by this term. So D2G HS1, HS1, that has to go like 1 over R squared, purely because of the form of HSS. So this is integrable. It's valid across the full domain of the space-time. And if we move to the HSR piece, although it goes like 1 over R, meaning that when acted on by dg, it goes like 1 over r cubed, it is in fact, you can define it as a linear operator acting on an integrable function. This means that although 1 over r cubed is not integrable, because we are acting with a linear operator on an integral function, this is valid as a distribution. So we can write our second-order Einstein field equations as so. And then in fact, because all terms are well-defined as distributions, we can promote this to include a stress energy tensor on the world line, a second-order stress energy tensor. And this we derived in our previous paper. So how to implement in the puncture scheme. So the expressions we derived for the perturbations were all in Fermi-Walker coordinates. So these are coordinates tethered to an accelerated world line, where at each value of proper time, you generate a surface with a radial unit vector and a radial distance r. So we can make it covariant using the techniques from Pound and Miller from 2014. This was for Lorentz gauge punctures in self-force, but the method is entirely applicable to the highly regular gauge. And then to implement in a puncture scheme, so for a puncture scheme, we truncate the singular field at some order in R, and then we use this local approximation to as input into the Einstein field equations to solve for the residual field. This is this curly R here. Now, if we've gone to a high enough order in distance for the puncture field, then this residual field will be exactly the same as the regular field. So we can solve for the motion of the particle and the space-time that the small object sees. So you have to solve these three this system of coupled equations. So I'll give a quick overview of the method. So we want to express a point in the field so this x here in terms of a point nearby on the world line x prime. So first we do that, we write x in terms of x bar. So this is a point where if you would shoot out a geodesic orthogonally from x bar, you would hit x. And then we want to re-expand, and then x bar is related to x prime by some difference in proper time. So how do we go about doing that? Well, the Fermi-Walker coordinates have quite a nice natural relation to a tetrad along the world line. In fact, we can write our Fermi-Walker coordinates t and x in terms of the proper time at x bar, and the tetrad leg contracted into this sigma here. So this sigma here is a derivative of Singe's world function. There's a nice explanation in this review article by Poisson et al. That gives details of it. But essentially, sigma is a bitensor. It's a function of both x and x bar. And it gives you essentially half the geodesic distance squared between x and x bar. So you can think of the derivative essentially giving you the geodesic distance between these 2 points. And then we can just make a simple substitution for the distance and the radial unit vectors as so to re-express everything at x bar. Now we're at x bar. How do we get to x prime? So we just perform we just do an expansion in powers of delta tau. So in the difference in the proper time between the two objects. So for example, the HTT component would be as so. And then we can re-express all quantities in terms of powers of Singe's world functions. And we can introduce some shorthand notation here to give a notion of the difference of proper time and spatial difference. So unfortunately, the expressions are too long to be included here, but we've checked most of them. There's a few little things we need to sort out, but we're in the process of checking those. And then to really make this useful, we want to write this in a specific coordinate system. So we re-expand all the covariant quantities in terms of coordinate differences. And this can be done using a variety of different identities. So for example, for Singe's world function, you have this identity here, where the derivative squared essentially is twice Singe's world function. And then, for example, this gives you a relation between Singe's world function and the coordinate differences. So you end up with a coordinate puncture purely in terms of the metric derivatives and delta x and u. So today, I've outlined benefits of the highly regular gauge. I've demonstrated the conversion into covariant and coordinate forms. We're just in the process of checking those. And these expressions will be available online and in an upcoming paper for other people to use. Thank you very much.
All right, thanks very much, Sam. Again, we don't yet have any questions from the audience. So let's see.
I realized my camera was not working properly. Sorry about that.
Sorry, yes. When you asked if we could see you, it took me a few moments to realize that, in fact, you were completely invisible. We could at least see your slides.
Good.
Any other questions from the audience? Okay, I think we will allow anybody to ask you questions on the Slack channel.
Sure.
And so that we can keep to time, we will move on. But again, thanks very much, Sam. Very interesting. Next up, we